In this video, we're primarily going to focus on the multivariate normal distribution, but before we do that, one special case of the normal distribution, or as we call it, the Gaussian distribution, or the bell curve, is what we call the standard normal distribution. And standardization is a mathematical process. In statistics, the standardized version of the normal distribution is where you have a mean of 0 and a standard deviation of 1. And here's what that looks like. You can see that almost all of the distribution is located between about -3 and +3 on the x-axis. This is just a very convenient distribution to work with. In fact, up until technology became quick and accessible, the way that one would look up probabilities in the normal distribution would be to actually look at a table in the back of a textbook, which would be in the standard normal form. And regardless of what version of the distribution is that you are working with, you could always standardize it and then use the lookup table to find probabilities. So anyway, that's one of the conveniences of working with the standard normal is everything can be converted into the standard normal and can use one probability table. I just wanted to put that out there. But let's focus here on the multivariate normal distribution. And this is really just, here we have a vector of random variables x. And so again, maybe the measurements that we have on a bunch of people, maybe their age. So maybe we have a 22-year-old who is 68 inches tall, and has all of these variables, and then maybe the last measurement is their weight, and maybe they are 165 pounds. And so here we have random variables, and for each person we would have a vector of measurements like this, and we perhaps have a reason to believe that the distribution of all these random variables is standard normal. Now this might look awful, and for a moment it does, but notice how remarkably it resembles the normal distribution for one variable. In fact, if x were to be a 1 by 1, in other words, it's just a single entry, if x is 1 by 1, then look at what happens here. I should add the fact that x is an element of Rd. So in general, this is going to be some d by 1 vector. Okay, and we need that because the value of d is going to come in play here. So if d is 1, then you would have 2 pi to the -1/2. Well, -1/2 is a negative power is 1 over that raised to the positive power. So it would be the square root of 2 pi. Now, we recall that the sigma matrix has the variances in it. So if we are talking about a 1 by 1 variance covariance matrix, well, it's only applicable for the variance between x and itself, or the covariance, which would actually be sigma squared. And so if you take the determinant of a 1 by 1, by the way, if you have sigma squared in here, the determinant is exactly that one entry. Okay, so we get just sigma squared. Now, because it's sigma squared to the -1/2, that's 1 over sigma squared square rooted. So because these are multiplied together, I can put the sigma squared down there. Now here we have e to the power of. Now once again, notice that here we'll just have -1/2. The x vector is just a single element, and mu is just a single element. Okay, so that would be the transpose. Again, here we would have the inverse of the variance matrix. And by the way, the inverse of a 1 by 1 is precisely just the reciprocal of that 1 by 1. So we get 1 over sigma squared. And here we have x minus mu once again. Now, when we transpose a 1 by 1, it's still the exact same 1 by 1, so we don't really need the transpose here at all. And so that leads us to 1 over the square root of 2 pi sigma squared, e to the power of, now let's simplify, we have negative 1/2. We have x minus mu times x minus mu, which is x minus mu quantity squared. Again, just because that's a scalar. We have negative 1 over, and then we'll have 2 sigma squared. And that is precisely the univariate normal distribution. Now let's look at and by the way, if the mu vector, so now going back to the idea that this is going to be a d by 1, if the mu vector is a d by 1 vector of zeros and the variance covariance matrix is the identity, then you have the standard normal distribution. Remember, like in a 2 by 2 setting, the identity would be 1, 0, 0, 1. And sigma, or mu equal to 0 would be 0. So notice that this would actually be the standard deviation between, the variance and standard deviation between the first variable in itself. This would be the variance between the second variable in itself, and the covariances here would both be 0. Okay, let's take a look at an example of a similar situation. We have a mean of 0 and for random variable 1, I'll call this mu1 is equal to 0, and sigma 1 is equal to 2. Sigma 1 squared. And then mu2 is equal to 3, and sigma 2 squared is equal to 3. So a little more variance in that second random variable. And in this case, this is that x1 and x2 are independent and identically distributed, because this right here would be the covariance between x1 and x2. This right here would also be that same covariance. That would be the covariance between x2 and x1. And so that would mean that we have independent random variables, because if you recall, if there's no covariance between the two variables, if they don't covary, then they're independent. And they're identically distributed, meaning they are both normal. Both normal. Now, the way we would often write this is we would say that the x vector, the vector of random variables, which there are 2 of in this case, is distributed, and we would say IID, as a normal distribution with mean vector 0, 3. We always state the mean first, and variance covariance matrix 2, 0, 0, 3. So that means the exact same thing as what we set up here, just in a more compact notation. So what would this look like as far as this is concerned up here? Well, it's quite simple for this example because of the 0 covariances. So given the mu vector and the sigma matrix, again, that's what we need to fully specify the distribution. Okay, so here we have d is equal to 2 because we have a 2 by 1 vector, and this would be negative 2 over 2, which would basically just give us 1 over 2 pi. Okay, because that's being raised to the negative 2 over 2, which is to the negative 1, which is simply the reciprocal. Now, the determinant of this sigma matrix would be the product of the diagonals, 2 times 3, minus 0 times 0, which would give us 6. Okay, so that's 1 over the square root of 6. It's raised to the negative 1/2. So we have 1 over 2 pi times the square root of 6 in the denominator. And then we have e raised to the power of. Okay, so we'll have negative 1/2. Here we'll have in the parentheses x1, x2 minus the mu vector 0, 3. That quantity transposed multiplied by the inverse of the variance covariance matrix. And by the way, this is a diagonal matrix. The fact that the above and below the diagonal is from top left to bottom right. Because these are zeros, the determinant in this special case will simply come out to the reciprocal of the diagonals and then zeros. Now remember, this is only true for this matrix. That's why I picked this. And that would give us the inverse of that matrix. In fact, if you multiply these two together, you should see that you get the identity. And then once again, multiplied by the non-transposed x minus mu vector. Okay, so let's multiply this out and see what this gives us. So this equals 1 over 2 pi square root 6 e to the power of. Here we'll have x1 minus 0, x2 minus 3, but that gets transposed into a row. So we'll have negative 1/2. We'll have x1 minus 0 and x2 minus 3 times this 2 by 2 matrix divided by, now this is just going to be x1 minus 0 and x2 minus 3. Now what I want you to notice, dimensionally speaking, is that we will end up with a 1 by 1 because this is a 1 by 2 multiplied by a 2 by 2 multiplied by a 2 by 1. The inner dimensions match on both multiplications, and we're going to end up with a 1 by 1 scalar here. So if we do that multiplication, it doesn't really matter as far as which two of these we multiply first. We just can't change the order. I'll go ahead and multiply this vector times this matrix. And what that will give us is parentheses, I'll say dot, 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 negative 1/2 x1, x2 minus 3. And then when you multiply these, we should get a 2 by 1 vector from just these two multiplying together. The top component will be 1/2 of x1, and the bottom component will be 1/3 of x2 minus 3. And then when you multiply these two quantities together, these two vectors, you'll get negative 1/2 of, this will be 1/2 x1 times x1, which will be 1/2 x1 squared. And then the second multiplication here will give us plus 1/3 x2 minus 3 squared. Okay, and so you can kind of see that structure of the standard normal distribution where, notice in the top, in the exponent, we had x minus mu squared. And it's over 2 sigma squared. Well, it kind of is, right? Because here's sigma, sigma squared. Those are the 2 and the 3. Here we have x1 minus 0 quantity squared. Here we have x2 minus 3 quantity squared. And you notice that they get added together, and it's all divided by negative 2. So it actually turns out that here, when we put these distributions together, the means and the standard deviations, variances combine. Okay, and that would be our function. So let's go ahead and take a look at this. So here I've just gone ahead and entered in that PDF, that probability distribution function, and here you can see it. And I'm using, in this case, x for x1 and y for x2. So if we recall, x, if you just take a look at it by eliminating the y direction, then we have a perfectly nice standard or normal distribution with mean 0 and variance 2. Okay, so look at this for a moment, and then as I rotate this into looking at just the y-axis, this random variable has a mean of, what do we write for the mean? The mean is 2 in this case, and the variance is 3. So and then the reason these look so spread out is less spread out is just because of the scaling. So I just changed x and y to go from negative 10 to 10 in both directions, so that we can see that there's the mean 0, smaller variance, mean 3, bigger variance, more spread. And so when you put those together, yeah, you have this kind of like bullet point, almost like a traffic cone, right? And there's your standard normal distribution. In fact, there you could even see the variance is bigger in the y direction than it is in the x direction. And once again, what we should point out is that if you take and you integrate this from x goes from negative infinity to positive infinity. dx1 of f of x1, x2. Okay, I'm just going to write it that way without the given mu and sigma, because we already know it depends on those. And then also, if you accumulated all the area, or rather this would be a volume calculation, but if you looked at both cross-sectional areas, you'd accumulate volumes, and guess what the volume should be? Well, it should of course be 1, because the probability that anything from negative infinity to infinity happens is guaranteed. Finally, if we have pairs of multivariate normal random variables, right? So here the idea is kind of weird. It's like, well, wouldn't we just take those random variables and put them into one vector? Well, here we have x is a multivariate normal random variable with n sub x states. Okay, so this could, for example, be let's just look at the example of where we have a 2x1 vector. So every measurement that we take has 2 states, and maybe this one is a 3x1, and so this random variable has 3 different states, 3 different measurements that we take on it. And so if you think about what this would be, this normal distribution, I'm not going to write out the PDF of it because it does get a little cumbersome, but the mean vector would contain mu sub x, well, that would be 2 components, and then mu sub y, well, that would have to have 3 components. So notice that this would be a 5x1 vector of means, right? And so then what we would have here in the variance covariance matrix is we would have the covariance between x and itself, and that's going to be a 2x2. The covariance between y and x will be a 3x2. So notice you'll have a total of 5 rows, and this will give us 2 columns, but then also over here, the sigma sub xy will be a 2x3 variance covariance, because it's x along the rows, y along the columns, and here y will be a 3x3. So notice that in total, this will give us, we have each of these has 2 rows, 3 rows, so that'll be 5 rows. And then here we'll have 2 columns, here we'll have 3 more columns, so this will be a 5x5 in this case. And so that just amounts to having more variances and more covariances in that matrix.